Hi everyone, I'm Pierre, I'm the CEO and co-founder of C12, and I'm very pleased to be here. It's the first time I travel to Japan, and so it's the first time I will introduce our very unique technology to a Japanese audience. So very pleased to do so today. So I will share first our vision, a few facts and figures about our company, and then how we can try our technology today. Then a few slides about maybe the physics behind this very unique approach. No other quantum hardware technology is developing carbon nanotube based qubits. And I will open up at the end of my talk about the next steps. We don't have quantum computer yet. We don't have them yet because they are bugged with errors. We don't have them yet because it's even worse when we increase the number of qubits, the error rate goes up. And all this error, they come from defects in the qubit material. And now there is a large consensus, both in the scientific community and in the quantum industry, that if we want to build a large-scale quantum computer, we need a breakthrough in terms of material science. We need a material that enables to have much better qubits in terms of quality than what we have today. And the breakthrough is coming from a very simple material, carbon nanotube. Carbon nanotube is the most minimal electrical wire you can imagine. And the core know-how of C12 is to transform this carbon nanotube into quantum transistor. The results with this incredible material is that we are able to build a large-scale, fault-tolerant quantum computers without any roadblocks. So if you take any criteria that a quantum computer needs to fulfill to be large-scale and fault-tolerant, be it on qubit quality, on ability to scale, speed also of the gate, we are all with a high rate on those criteria. So there is no blocking point for building a large-scale, fault-tolerant, carbon nanotube-based quantum computer. Our vision is that all big revolution in computing starts with a material breakthrough. And it was not obvious at all in the late 50s, early 60s, that silicon was the material to build the semiconductor industry. And it's probably also not obvious today that carbon nanotube are actually the best material to build quantum computers. And the big analogy is that the fundamental properties of those two materials were actually adequate to build this kind of application. Silicon for semiconductor chips and carbon nanotube is the best material to make high-quality qubits. What was missing was the manufacturing process. I will also introduce how we are building carbon nanotube-based quantum computer. So a few facts about C12. We are Paris-based quantum startups. We are been funded in 2020. We are now close to 50 staff, primarily R&D, and also we are a success in several world-first research results. It's a family business. I founded C12 with my twin brother. So my twin brother is the scientific genius behind this technology, and I'm in charge of all the management and business of the company. And we also have recognized scientists in the field of spin qubit physics, and also many business advisors. One of the core assets of C12 is that we have our own quantum fab. So we have our own quantum foundry, more than 1,000 square meter in the center of Paris. We have our own clean room, and so we can have very short iteration loop to build our quantum computer. And then it's a moment to go a bit more inside how we are fabricating those quantum computer. So you have kind of two parallel steps. The first one is building the IC chip, where you have all the circuits to initialize, control, and read out the qubits. And on the other side, we are making the core component of our quantum computer, where you will have the qubits, the carbon nanotube. So we have built very unique know-how in how having an extremely well-controlled fabrication process of those carbon nanotubes. And then we have this key step just after the fabrication of the carbon nanotube, where we have like a quality control and selection of the carbon nanotube. So we are able to really select individually this nanomaterial, and it's some key know-how that we have built in the company for all those years. This is very important because in a way we are then with this technology the only technology that is able to pre-select the qubits and not relying on post-selection. And then we have the last step, which is the manufacturing breakthrough that enable the scaling of this technology. It's a patented process. It's a nano-assembly process, and it's the moment where we integrate the carbon nanotube on this silicon chip. So what is important is that because we are based on a silicon substrate that can be actually manufactured in like standard silicon foundry, this is also a very important point to scale our technology. So we are still on our R&D phase, working on 1 and 2 qubit chips, because what we think is that for the moment, what matters is not about the quantity of qubits, it's really about the quality. So we are really focusing on making the much better, much higher quality qubits. We still have released last year our first software product, Callisto. So Callisto is an emulator. It's really like a flight simulator if you want to learn how to fly a plane. In this case, it's an emulator if you want to start your quantum journey. So Callisto, we made it also very different from what you can find out there in terms of simulator. So it's hyper-realistic model of how qubits behaves. So what we program into Callisto is all the quantum phenomena that are occurring during a quantum computation. And all also the sources of errors are actually programmed into Callisto. So it's extremely realistic. Then you have like a direct link between really the result of running an algorithm on an emulator and the physical parameter of our chip. And it's compatible with all the software development kits that you like to use, be it Qiskit or Tkit or any other software development kit. Here are a few actually different channels that we model into Callisto, like the charge noise or the phonon noise, or also the relaxation through the resonator. So Callisto is already available. We have a first version out, 13 qubits, based on our very unique approach of carbon nanotube qubits. You have high fidelity gates operations, and we also add a few other interesting features like mid-circuit measurements and also noisy initialization. So you can check out our website, and then you have direct access to Callisto through our website. Now I will take a bit of time to really go into our technology. Usually I like more to present what we can do with quantum computer and what we can do with our technology. But as it is the first time that I have the opportunity to present C12 to a Japanese audience, I really wanted to share also a few information about how this unique approach is working. So here is a carbon nanotube, and this is where we trap a single electron, and our qubit is encoding on the spin of this single electron. And what is great about this carbon nanotube is that first, we are able to isotopically purify the carbon used to produce this carbon nanotube. So that's why, compared to any other spin qubit technology, we have only between 0 and 1 nuclear spin per qubit. So very, very low decoherence coming from nuclear spin. We have also like this, at the end, it's kind of a macromolecule. So it's mostly vacuum around the qubits. And this enables to have very low susceptibility to charge noise. Actually, we were even able to demonstrate that with the carbon nanotube, we have the world record in terms of charge noise for spin qubit. And the last thing is also that it's a 1D system, so you have a very defined vibration mode, mechanical mode, like phonon, and we are able to decorrelate from any of the phonon-induced decoherence. So this is a very simple sketch on how our architecture is looking if you really zoom into our chips. So you integrate, you encode the qubits into the single spin of the spin of a single electron that is trapped through semiconductor gates. And as I mentioned, we really like has the best material to protect from any kind of perturbation. Magnetic perturbation, I mentioned the nuclear spin. Electrostatic perturbation, I mentioned that we are world record to protect against charge noise and mechanical perturbation. So that's why last year we were able to demonstrate our first qubits with world record concurrence time. So we were already achieved a 1 microsecond concurrence time. It was a very good start for our first demonstration. Of course, it's just the beginning of what we can do with this technology. And what is already extremely promising is that both T1 and T2 star are above the microsecond. And this is really rare for any quantum technology. It means that we really are able to protect the qubit from any kind of errors, be there bit flip error, T1, or phase error like T2 star. So here is the nano assembly process. It's really something that is completely a marvel in terms of engineering. At the end, we are able to assemble materials that are at the nanoscale. A carbon nanotube is a diameter of 2 to 3 nanometer and only like 10 micron long. And we are doing this at a very, very also fast scale. So we can have like this kind of nano assembly process up to a few thousand carbon nanotube per hour. Here also, it's often a question I have, like how we control the spin and how we couple spin qubit together with this architecture. So we have introduced a very important component, which is quantum bus. And this quantum bus enable us to actually have photon-mediated 2-qubit gates. The last maybe important point is how scalable are we? We are scalable because we are a semiconductor integration, so we have like possible to have very high qubit density. In terms of quality, as I mentioned, we are relying on pre-selection, which is, I think, the only way to really have high yields in terms of chips fabrication. And so for quantum error correction, we have like 3 assets: the high qubit density, the connectivity, because of this quantum bus, and also the very high quality. It's really what is the core of our value proposition, is to make much higher quality qubits. A few words to finish about what's next. So as I introduced, C12 is really a new way of building quantum computers, ultra clean material, and we really have the profound conviction that if we want to make a large-scale quantum computer, we need a breakthrough in terms of material, scalable fabrication, and a high connectivity. What we are developing is mostly the hardware and the control, low-level control software, so we are not full stack. And if you are quantum startups developing software, if you are developing quantum application, you have a very easy way to integrate with C12 and developing your application on top of our hardware. And we have already started to work with first customers. And as also JC mentioned just before, the quantum journey starts by identifying key use cases that will have like unlock a lot of value for your business. And this is what we have started to do with Air Liquide, which is one of the largest chemical producer. We partner for this kind of project with experts in quantum application. In this case, it was Quantinuum. And we were able to really identify one industry-relevant use case and simulate it with using Callisto, the quantum emulator I just presented. So in terms of dates, our first hardware will be released end of 2025. We will start with the 5-qubit quantum chips, and then we will scale both the number of qubits, but also demonstrate error correction, and then to finish with error-corrected full-scale quantum computer, having demonstrated both error correction and a scale number of qubits. Thank you very much for your attention and to listen to this introduction to this very new way of building quantum computer. Thank you.
Thank you. We have a little bit of time for questions. Thank you to the audience who have been sending their questions. First question is, what is the physical size of the nanotubes? How does it compare to other platforms, and why do you think it has an advantage in scalability?
So it's really a tube. It's tube made of a single layer of carbon atom. And with this material, you can think that you are actually making at the end the closest realization to a spin qubit in vacuum. And so we are kind of solving this like quantum paradox, where to have the best qubit, you need to have a qubit that is both extremely well isolated and very well also connected and addressable. And so that's why that in terms of quality, it's the best material to make qubits. And in terms of scalability, it's all about the compatibility with standard semiconductor fabrication processes.
And also, what is a typical single and 2-qubit gate time?
So the single qubit gate time is around 80 nanoseconds. And for the 2-qubit gate time, for the moment, we are at 500 nanoseconds, but we think that we can also be even faster. Thank you.
One last question, actually. Could you elaborate on the realization of 2-qubit gates? Do you need to design larger footprints for it? Larger footprints for it?
No, we won't need a larger footprint. So what, in terms of footprint, what takes the most space in our layout is the quantum bus. But this is where interesting is that to the quantum bus, we can actually connect more than 2 qubits. So thanks to this quantum bus, we can have like high connectivity between a placket of qubits. Thank you.
Excellent. Thank you very much.